Good morning. Welcome to Mass 206. So this is the seventh lecture in this course. So far we have been talking about normal subgroup. I think the last time we discussed the concept of normal subgroup. Say a normal subgroup is a subgroup where every left coset is also equal to a right coset. That is, there is no distinction between left and right cosets. You can still remember the definition. And then we look at some properties of this normal subgroup. Like one of the things we did in the last part of our discussion is to look at the concept of multiplying the coset. You remember we say given two cosets, n1 and n2, you can multiply them together to get a new coset, and the new coset you arrive at will be the coset generated by the product of A and B, NA1, NA and NB, and the product will be NAB. That is the coset generated by the product of the individual generators of this particular coset. And this happens precisely when the subgroup is a normal subgroup. That is, a subgroup of a group is a normal subgroup if and only if the product of any two left coset is also a left coset, or the product of any two right coset is also a right coset. I'm writing left, right. You know, there is no distinction between left and right in the concept of when you are dealing with normal subgroups. Okay, so today we are going to build on from that point where we stopped. So we start by looking at a collection. So we say let N be a normal subgroup of a group G. And denote by Gn, G by N. So let G by N be the collection of all right cosets. G by N, the collection of all right cosets. But this is still a set of N in G. This will still be a set. Okay? And so we can define on this set a binary operation. And we have a natural candidate for defining a binary operation on this set. Remember, what we are trying to do is to create a group structure out of this particular set. So since it is a set and we want to make it a group, we define a binary operation. And the natural candidate is to define the product of two right cosets to be equal to the right coset generated by the generators in this way. Then we define the product of two cosets it's not necessary that we should always continue to be saying right coset, because this is normal subgroup. Every right coset is also a left coset. So a product of two cosets, NA and NB in G and G by N. This is our set now as NA multiplied by NB to be equal to NAB. Now what we want to see is that this particular product is satisfying the axioms of a group. So we will do that here. So first of all, we have to see that the product is well defined, because it should be a binary operation. That is a mapping from G by N cross G by N into G by N. So what I mean by well-defined is that if I know one element in the Cartesian product will be mapping to two different elements in the group. So, so first we see that this multiplication of coset, that is the product of coset, is well defined. So that is, if NA is equal to NX and NB is equal to NY, then the product of NA with NB should be equal to the product of NX with NY. So we must have this. This should happen, because if these two cosets are not the same, then we are saying the same pair is mapping to two different product, two different cosets. But that means it's not well defined, because if you are talking about a mapping, remember when we say binary operation should be a map from the group G, a set X into X cross X to X. And that means it is taking a pair XY and mapping it to the output, let's say XY. So in the event where this pair is the same thing as X1 and Y1, but then this will still be mapped to. So if XY is equal to X1 and Y1, and then the mapping or binary operation will send it to X1, Y1. But if it happens that XY and X1, Y1, that is the two images are not the same, then that means a single element is mapping to two different images. So the mapping will not be well defined, so it will not be considered as a function. So for the binary operation to be well defined, we must have this to be true. But then that is true already, simply because of the fact that we are dealing with a normal subgroup. So that is already true, since we have a normal subgroup. So one can see that it is true. This is true since if NA is equal to NX and NB is equal to NY, then I can cancel X from here, so that I have NA X inverse equal to N. And I can have NB Y inverse equal to N. And that means AX inverse is an element of N, because if NaN inverse, NaX inverse is equal to N, then this element generates the same coset as N, the same coset as the identity. But that means the element is a member of N, okay? Since the coset generated by the element is equal to N. And this is how we see it. And also, it is true that By inverse is in N. So that if you now look at the product, so if you look at the product AB XY inverse, so if you want to achieve this, you have to show that the product XY, that is the coset generated by this product, if I cancel this from this side and I cancel XY from here, so the coset generated by AB times XY inverse should be equal to N. But to do that, I have to show that this product is inside N. It's an element of N. So that is what we want to show. So I want to achieve this to be an element of N. So this should be equal to AB well, A, B, Y inverse, X inverse by, this is a very basic principle of inverse of product. We have been using it many times. So here I can introduce X inverse, X, by inverse, S inverse, because this is just like identity over there. And so what we have here is A inverse, A X inverse times X by inverse, and then we have X inverse like this. And because of the fact that this element is in N, so this is an element of N, and this will also be in N because the middle element here, by inverse, is in N. And X is just any element coming from the group. So, and whenever you do this, you sandwich an element with, take the conjugate in this way. That is, an element of N, multiply by X with X inverse, where X is coming from the group. This is the requirement for a subgroup to be a normal subgroup. So for all G, and for all N, G and G inverse should be in N. So since this is in N, by normality of N, then the product of two elements of N will still be in N because N is a subgroup. So this result we obtain to be an element of N. So therefore it means the product here is true. Okay, so what we have is that NAB is equal to NXY. So the multiplication or product of coset is actually well defined. So this is showing us that the product is well defined. So we have a binary operation on this set of cosets, right? Coset or cosets. So to see that this is forming a group, the set G by N is a group with the coset multiplication. With the coset multiplication, we establish the four properties or three properties. That is, we have to see that there is associativity property is happening. So if you take 3 points from there, so if we so the first is to check that you take X, well, if you take X to be equal to NA and the Y to be equal to NB and Z to be equal to NC in G by N, because every element coming from there is a left coset, then is a coset actually, then X, Y times Z will be equal to, by the very way we define this, this should be NAB times NC, because the product here is NAB and then NC. But this would be NABC. And already associativity is happening in the group. So what we have here is ABC. I perform associativity in G, and that would be NA times what? NBC. But you would now see that this is X and this is YZ. So the multiplication of coset is associative. It's indeed associative. Then we can now see that the next is to see that there is an identity element existing. So the coset N, which is equal to NE. No, the normal subgroup itself is already a coset. And that's the coset generated by the identity. Is the one that will act as the identity, in G by N. since if you take any coset of that nature, multiply by n, you arrive at the coset. So since for all a in G, n times, so ne times na will always be nea, and that is equal to na. And na times ne is also nae, which is na. So always, so that means this is acting like identity by the very definition of identity. Okay? The third property is to see that there are inverses. So for each x equal to na in G by n, we have always, because this is consisting of all cosets or right coset, so always corresponding to every na, there is this y, which is na inverse in G by n, because it is also a coset generated by the inverse of the generator of this particular coset x. Okay, and so with this property that x times y would be equal to n a inverse if you do the product, but that is ne, which is n, the identity that you have identified. Are you following? So, and yx will also be equal to n. So, which means corresponding to every element there is the inverse of that particular element in the set of all cosets. So, but these are all we require for a set to be a group. Okay, and so therefore it is a group. That means G by n is a group with respect to coset multiplication. So we have a theorem. So what we have just proved is the following results. I don't know, from the last time I was numbering my results, what was the last number? The last lemma we numbered as 3 point what? 3.4. 3.4. So this should be 3.5. Okay. So we say if n is a normal subgroup of G, then the set of all cosets of n, the sets G by n of all cosets. You can just say coset, it can be left or right coset, they are all the same. So I can say right coset of n in G is a group under coset multiplication. Given by NA, NB is equal to NAB. The proof is what we have just discussed. Is that okay? So we now make progress. Maybe let me give you an example of this kind of thing. So, well, the group is called, it has a name. It has a name. It is called the Quotient group. Okay? Of n by G. So let me just define it. The group G by n, just define with respect to coset multiplication, is called the quotient group. Or sometimes it is called factor group. So it's called the quotient group or factor group. Of G by n. So actually what this group is doing is like it is dividing the set into classes. It's like it's dividing the set into classes, and that is what it is doing. So that's why it is called quotient group, just like you are dividing G by N. You can recall that the order of the group is what? The index of N in G. Remember? From the Lagrange's theorem, if G is finite, then this group is of order the index of N in G. If G is finite, then the order of G by N is given by the index. So it is the order of G by N. It's just the order of G divided by order of N. You know, this number is called the index of G of N in G by the index of N in G. Yeah. Okay. So let me give you an example of this. So we can consider the group G equal to Z. That is the group of integer. And addition of integers. And let N be the subgroup of, I can take 3Z. That is the subgroup of the group of integers consisting of all multiples of 3. Okay? Then the coset, the left coset or coset of N, because this is a normal subgroup automatically because the group is abelian. So, and we mentioned it that if the group is abelian, every subgroup is already normal. So the coset, the coset or right coset, you can of N in G. So, well, first of all, you have the group itself, the subgroup itself is always a right coset. Well, so N, that is 3Z. Okay? And then the next subgroup will be 3Z plus 1. So this is N plus 1. It's like the subgroup generated by 1. You know, here you have all multiples of 3. So the set consists of things like -6, -3, 0, 3, 6, and so on. 6, 9, 12, and so on. All multiples of 3, because if you, it's closed under addition, this is a group. Okay? So to generate a coset, you look for an element outside of this particular coset, because this will still be the coset generated by 3. 0 is the identity of the group. It's also this coset generated by 6. We have talked about this. Okay? So if we take 1, it will generate a different coset. And that will be the coset generated by 1, this particular one. And what will be the element? So it's like you are adding 1 to each one of these elements. So it's like you are saying 1 and then -2, minus what? 5, and so on. Cool? And then you have 4, 7. These are the elements. And then the next one, because 2 is not appearing so far, so 2 will still generate a new coset for us. So the new coset generated by 2 will be this one. And that will be consisting of, well, so you add 1 to the element of N. Are you following? You add 2, sorry, 2 to the element of N. This is how you define it. So you have 2, and then if you add 2 here, you get -1, -4, and so on. And then I have what? 5, 7, no, 5, 8, and so on. But then so far you will see that all the elements of the group are exhausted. Because you have 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on. Okay? Minus 1, minus 2, minus 3, minus 4, minus 5, and so on. So you see that the union will give you the entirety of the group. So actually, if you unite all the elements of G by N, you will get the element of G, because this is a partitioning of the group into coset classes. That is congruence classes. So then it means G by N in this case will consist of this element 3Z plus 1 and then 3Z plus 2. Well, you know, the usual convention in number theory is to call this one, you know, the congruence modulo class of 0. We normally write it as 0 bar. Oh, and then that is written as 1 bar and 2 bar. So you think of the element as this. But then no problem, let me just see this as the coset. So this is like n plus 0. That is the coset generated by 0. And that is n plus 1. This is n plus 2. This is a group. You can have a small multiplication table for this coset multiplication. You have 3z plus 1. You have 3z plus what? 2. Then you have 3z, which is your n, 3z plus 1, and then 3z plus 2. But then, well, it will be addition here. And addition means you add the generators. So if you say this multiply by this, so it's going to be addition, and addition modulo 3, because the group will be doing addition modulo 3. So this is 3z plus 3z. You remember how we are doing it? So if you have NA, NB, it should be NAB. So you concentrate on the generators. So it's like 0 plus 0, because this is 3z plus 0 and 3z plus 0. I hope it's okay. Let me write the 0 so that it will be pronounced. So 0 plus 0. So you have 3z plus 0, and then 3z plus 1, 3z plus what? 2, because you are adding with 0. Now over here you have 3z plus 1, 3z plus 2, and 3z plus, this will be plus 1. 1 plus 2, and that is 3, bah? But 3 is an element inside this class. So it's the same thing as plus 0. Are you following? Because, so that's why I say addition modulo 3. Okay? And then 3z plus 2, 3z plus 0 again, because 2 plus 1, and then 3z plus 4. And 4 will be in which class? In the class of 2, of 1. Okay, so that will be plus 1. So you can see that this is actually a group. This has an inverse, and the inverse is 3z plus 1. So the inverse of 3z plus 2 is 3z plus 1. Meanwhile, 3z is our subgroup. Are you following? So you can see that operation is closed, inverses are there, associativity is immediate. So it's a group. So we have this kind of thing. Okay. So that is what we wanted to achieve studying normal subgroup. But then we now talk about a very important concept in group theory, in fact, in the whole of abstract algebra in general, and that will be the concept of homomorphism. So we say group homomorphism. Group homomorphism. So group homomorphism is a concept very closely related to the concept of normal subgroup. And this is the concept of having structure preserving mappings between group. This notion is common in all abstract algebra, throughout the study of algebraic structures or algebraic systems. The concept is always available. So, and that is the concept of structure preserving maps. But so what is the advantage of having structure preserving mapping? Is to be able to identify which groups are similar, or which groups are the same. Because at times you will not be able to say whether groups are the same by merely looking at them. You have to do some extra work to be able to decide whether they are the same. And that will be provided by the notion of homomorphism and the isomorphism of the structures. So we start by the definition of what we call a homomorphism. So to define a homomorphism is a mapping between two groups. So you need to have two groups. So you take two groups, G and G prime, be two groups. Well, since you are hearing this for the first time, I will distinguish the binary operation. So cycle is the binary operation of the second group, and star is the binary operation of the first group. So two groups, because a group is always with a binary operation. But then the convention we have been taking is to say that the binary operation is implicit and understood to be multiplication, so denoted by juxtaposition like this. But then for the sake of this definition, after which I'm not going to do that again. So there a mapping F, let me call it theta, from G to G prime is called a homomorphism. This is the notion. And if for all A, B in G, so for any two elements you pick from the group G, the product A times B, but then terms here, because we have already mentioned star is the binary operation. So the way to combine element here is using star. And if you combine, you get an output. Well, every element is mapped to an element. So you have theta A, theta B being element in this group. They can be combined using cycle. So the image of the product of the images. That is what this notion is. This is a nice map that preserve the group structure. That is the binary operation. So you can visualize what goes on here. You have the group G and you have the group G prime. You imagine an element A will be mapped to theta A. This is how we call the image under theta. And an element B will map to theta B. But then, since this is a group, if I combine A and B, I get a product still inside the group. And since we are talking about a mapping, every element of the domain must be sent to an image. So, and that image here will be the image of A star B. But here, we are still living inside a group. So element can multiply to produce a new element, and the multiplication is via the cycle operation. And so the product of theta A and theta B will still be living inside this group. So it is theta A cycle theta B. So what the homomorphism condition is saying, that the resulting product must be equal to the image of the pre-images, the image theta A star B, the image of the pre-images of this point. I hope it's okay. So you must have equality here. In the event where there is no equality here, that if the composition of this image and that image inside G prime happen to be a different element from the image of the product A star B, then the mapping is not a homomorphism, because it is not structure preserving. I hope it's okay. So if it is a homomorphism, once you know the image of A and you know the image of B, you already know what the image of the product will be. The product of AB inside the domain, you know what it must be. It must be the result of multiplying theta A and theta B. It cannot be any other element apart from that one. So this is what homomorphism is saying. And that is all. The immediate consequence of this definition of homomorphism, before I give you examples, is to say that where the identity element is also preserved, because one will wonder, you say it is preserving the group structure, and as part of the group structure there is identity. It's not only binary operation that is the structure available, there is identity, and there are inverses also. So all these are structures required for the group to satisfy. So what about identity? You wonder, so if identity is here, E, is it still going to identity in here, E prime, under theta? And how about the inverse of A? It will still exist here. So what will be the image of the inverse of A? So my first lemma will be to tell you that the images will be preserved. So this is 4.1 now. So in fact, identity is preserved and the inverse is also preserved. But from now onward, let me just make a remark that we are going to just be using, assuming that the binary operations are the same. So instead of writing this like this, I'll just say theta AB is equal to theta A, theta B. Well, meanwhile, it should be understood that the binary operation here is not the same as the binary operation over here on the right-hand side. Okay, why it should be different? Because here you are performing binary operation in the domain, in this group G. And here you are performing binary operation in the codomain, the group what? G prime. And they may not be the same groups. It may be the group of matrices. So you are talking about product of matrices. And this may be the group of real numbers. Okay, so you are talking about non-negative real numbers. Oh. So you are talking about numbers, multiplying numbers. Or this can be the group of non-zero real numbers. So product, and this may be the group of integers. So you are talking about addition here, integer under addition. So binary operation may be different. So it can be times here while you are dealing with numbers. It can be plus here. Maybe. I hope it's okay. Okay. So this operation can be anything, and this operation can also be any binary operation. So this is just the remark I wanted to. So lemma 4.1. So if theta from G to G prime is a homomorphism. Theta? A plus B. Where is theta A plus B? That we have theta AD. What is theta A plus B? Yeah, if the binary operation of the group is addition, then it will be theta A plus B. Because that means if here, this star can be any binary operation. This is what I explained. So it can be theta A plus B. And then the output may not necessarily be by addition. It can still be theta A. If it is multiplication, theta B. Are you following? Or it can still be addition, it doesn't matter. Because you can have a homomorphism from a group to itself. I hope it's okay. So if you have a group homomorphism, then theta of E would be equal to E prime, where E is the identity, while E and E prime are the identity elements of G and G prime respectively. And then the second thing is to say that for every element A in G, for all A in G, theta of A inverse will be equal to theta A inverse. That is the inverse of an image is the image of the inverse. Okay, it's not difficult to prove using only this condition. So this condition will imply the preservation of the other condition. So once the binary operation is preserved, identity will be preserved, inverses will also be preserved by the homomorphism. Well, here I assume I just say let it be a homomorphism, but since we are doing group theory, so it is understood that group homomorphism I'm talking about, and these things are group. Okay, or I can just say be a group homomorphism that has already pronounced G and G prime to be groups. Okay, so that assumption is already embedded in my pronouncement of group homomorphism here. That is okay. So proof. Well, this is very simple. It is just merely to check that if you take the identity, you will this will do the role of the identity. Okay, or you can use the fact that E prime is the identity. So for every, so you can just take, let A be in the group G and E prime as the identity. Well, I think I don't need to say that. Then, so I am assuming E prime is the identity and E is the identity in G, and E prime is the identity in G prime. So then if I multiply A, the image of A with E prime, I get A. Yeah, because that is what identity is doing. But here, this is theta A. Okay, and that will be because of the homomorphism property. So by the defining property of homomorphism, we have this. But then by left cancellation, this will imply that E prime is equal to theta E by the left cancellation in G prime. By left cancellation of what? Theta A. And you do this in G prime. So that is it. So you can cancel this since you are working in a group. Left cancellation means you multiply by the inverse of this and inverse of that. And that is all. Okay then. So secondly, we prove that the inverses are also preserved under homomorphism. So what to do is also to just take theta A and multiply with theta B, theta A inverse, and see that this is theta A inverse. But we have just proved in the here that this is the identity in the first part. And one can also see that theta A inverse, theta A is theta A inverse A, which is theta E. We have proved to be the identity from part 1. And which any element that is doing this must be the inverse of theta A by the definition of inverse. So it means the inverse of this element must be equal to theta A inverse. That is all. Okay, that's all. So good then. So let me give you examples of group homomorphism so that you have a feeling of the fact that they exist. They are group homomorphism. And the very first example I will give you is the fact that there is always a group homomorphism from every group into every other group. That is a very dull one because this is to have a group. So we just define from what? G, the group G to G prime by theta of x, whatever x you take is equal to identity for all x in G. This is a group homomorphism. Can you see that it is a group homomorphism? Yeah, because if you take any 2 points, xy in G, what will be the image of the product? yeah, if you take theta x and y, you get theta of the it is equal to identity by definition. Every element is mapped to the identity in G prime. But identity is identity times identity. Okay? But then the first identity you see as the image of X, and the second identity here you see as the image of Y. So it preserves the composition. Well, this product here is in G prime, while this product here is in G. So this is the trivial homomorphism. It's always existing. It's available always from every group to every other group. So it's like I can always shrink a group into the identity, put it inside, squeeze it inside every other group to become trivial, like identity. Okay? Number two, if we take the group of, let G be the additive group of integers. I can take the additive group of integers under addition. And G prime to be the group of multiplicative group of real numbers. I think this will still do. That is, yeah. So non-zero real numbers and multiplication. This is a group. Then the map theta from G to G prime. Well, my G is that one and G prime is this one, given by in fact, you could have taken, there's no need, in fact, you can take anything here, but no problem. We can take integral powers. So given by theta of x is equal to 2 to the x, like this. It's a homomorphism, group homomorphism. Why is it a group homomorphism? Yeah, we know that because we are familiar with the laws of indices. so it is a group homomorphism. So this group homomorphism is a generalization of the concept of these laws of indices and so on and so forth. But so it's because taking index to a fixed base is actually a group homomorphism, and that's why we had the laws of indices. So this is because theta xy, well, addition is our binary operation in the domain group because it is group of integers under addition. And that would be x plus y, 2 to the x plus y. But we know this from indices, it is 2x times what? 2y. That would be theta x, theta y. Yeah. Okay. Then we can have also the third example, maybe to say that if G, maybe the group of, let me still take this group, real numbers, but without zero. So under multiplication. And I would take G prime to be the group. I don't know that you can see this to be a group. It's a group under multiplication also. Okay? Multiplication of numbers. Then theta from G to G prime given by well, theta of x, if you take any element, a real number, non-negative, not zero, to be 1, if x is positive, to be minus 1 if x is negative. This thing is a group homomorphism. A group homomorphism. It's a group homomorphism. Can you simply check that it is a group homomorphism? Yeah. So maybe I will leave it to you as an exercise to check. But if you take two elements x and y, always one is there, either they are positive or negative. And so the product can be positive or negative. If at least one of the factors x or y is positive, is negative, then the product is negative. And if both of them are negative, the product is also negative. So you can see that I believe you can check it. Okay, can you do that? Okay, yeah. So for example, if both x and y are positive, then the product is positive and it is 1, and 1 is 1 times 1. And so therefore, what I'm saying, if both x, y are positive, x, y, if x is positive and the y is also positive, so you have to check it in cases like this. Yeah, so the product will still be positive. So, and it is 1, and this is 1 times 1, which is theta x, because x is positive. And that is also theta y, because y is positive. But if x is positive and y is negative, so what do you have? Theta xy, the product will be negative. But that is 1 times minus 1. You can use this one. But x is positive, so that is theta 1, theta x, and that is theta y, because y is negative. The other situation is similar. And for negative, negative is also similar. Because negative, negative, you have product to be positive, and which is 1, and minus 1 times minus 1. So it's actually a group homomorphism. So we have this example of group homomorphism. Well, the last one, and I will not also go into the detail, is to tell you that, so if you take the group to be the group of invertible matrices with non-zero determinants. Over the real numbers, you can take over R and take G to be the group of real numbers under multiplication. So maybe non-zero matrices. So I have removed the 0. So real numbers still under multiplication. And this group is also under multiplication of matrices. So you can define from G to G prime. So this is G prime. You can define theta from G to G prime by theta of, so you take a matrix and let it map to its determinant. Okay. Then this is a homomorphism. This is a homomorphism. Group homomorphism. Okay, homomorphism. Yeah. Okay. So this is this one. Okay then. We still have more time. We still have time? No time? So maybe we'll stop here. So, well, in the next class, we will look at this notion of group homomorphism. In fact, I will start by defining kernel of a homomorphism, and then talk about the linkage between group homomorphism and the normal subgroups. And we will see that the notion of the kernel of homomorphism and the normal subgroup are actually one and the same. That will be the point of start for our next discussion. Thank you very much for your attention.